All right, so this is the investigation. I believe you have tried some, so let's look at it together. Plot the graph of these pairs of points on the axis. So let's start with the first one. So basically the first part is talking about, not for the general class, it's just HL, sorry. So the first part is talking about the relationship. The idea of the investigation, like I told you in the module stuff, is you want to see how you can sketch the graph of the square of a function. Okay, if you look at the paper, the graph of f of x all squared. And the reason for this, just like we have done a sketch before, that of inverse. Now you know the relationship between a function and its inverse, geometrically. So you know what to do when you are given the graph of f of x without the equation or the expression, okay, that led to that. Okay, without that, you know how to get the inverse now. Similarly, if I give you the graph of a function and I'm requesting that you sketch the square of that function, that's the whole point. So I started with linear. Let's see. They meet somewhere. Okay, maybe we shouldn't take that seriously. Let's look at this. Are you noticing anything yet?
They share an x-intercept.
They share an x-intercept. Good point. Okay, let's see if that is true for these guys. Do they share x-intercept also?
Yeah.
Good observation. So they meet at x-intercept. So the x-intercept of f is also the x-intercept of f squared.
Yeah.
That's one good point. Another point,
They all meet at y equals 1.
they meet at y equals to 1. And the x-intercept is at y is equal to 0. So in my conclusion, I wrote that they meet at y equals to 0 and y equals to 1. Okay? That's two things. Those are two things. Y equals 0 and y equals to 1. So for linear, so what I did in my conclusion that I'm going to share with you now, I separated linear from quadratic.
Oh,
Okay? And of course, I put a general comment. So maybe I show you that also. You see? If it is linear, they meet at y is equal to 0 and y equals to 1. And you will notice something about the turning. The square turns at that intercept. Can you see that?
yeah.
So if you look at this one, that's the turning point. Okay? Again, they have a common y is equal to 0, y is equal to 1. The x-intercept is the turning point, or the turning points. Because if you are dealing with quadratic, there are two turning points. There are two x-intercepts. So if you look at the square, it has two turning points. At the minimum, there might be a turning point above. Can you see? Okay? It turns on the x-axis at that point, because there should be another turning point somewhere.
Yeah, because it's complete, a perfect square. So that,
It's not a perfect square. Oh, you mean the square one is this one? Yeah,
so it
yeah.
always touches the axis.
Exactly. Instead of going down. Yeah. Like none of them goes down because it's square.
Yeah.
So it will never be a negative. Okay? It will never be negative. So if you look at this, you see the graph of the rational function, remember, should be either in which quadrant or which reciprocal function. Which quadrant or which quadrant?
1 and 3.
1 and 3 or 2 and 4. But because we can never have negativity when you square the function, you will realize that the green is just above. Okay? It's just above. So, again, what do you notice about this? Any particular observation?
Well, I looked at it and I was like, oh, the domain is the same.
The domain is the same. Yeah.
They're the same.
The same asymptote. The vertical asymptote. Look. the vertical asymptote here is x is equal to 3, isn't it? So they share the same vertical asymptote. Let's check this 0 and 1 thing. When y is equal to 0, this is when y is equal to 1. Let's see, do they have the same? No. So that condition, I put it for linear and quadratic. I didn't put it for the general function. So for linear and quadratic, especially, check out for linear, let me say that. Expect that they meet at y is equal to 0. In quadratic, I added additional information if that exists. So if there is a y is equal to 1 value, then the square will also be at that point. Because if your y is equal to 1, when you square 1, you still get 1, right?
Yeah.
So if y is equal to 1 is defined in the original function, it is defined in the square as well. Does that make sense?
Yeah. Yeah.
So for here, they have the same asymptote. Where else do they meet? Do they meet somewhere?
No.
Let's see. This 4-1. Maybe there's a reason. Let's check the other one. 2-1. Are you noticing anything?
They meet at y equals to 1.
So yes, if there exists, because if the first one can give us a 1, then the other can also give us a 1. So that's why I said if there exists. Alright? But it doesn't mean that we will always have that. Let's see the exponential.
I noticed that you only said with the vertical asymptote, so it doesn't always share the horizontal asymptote.
I think it does. Our horizontal asymptote is as a result of, we have to be careful on that. Because if you have a function and you square it, the horizontal asymptote is that coefficient of y, isn't it? It's not guaranteed. Look at, imagine ax plus b over cx plus d in your head, which is a over c. If that function is square, you're likely not to have your a over c back. Right? So it's not guaranteed. That's why I was silent about that. Okay? It's not guaranteed.
Can you give us an example?
Okay, if we look at, I think we can see one here. For here we have 0, both of them are 0,
Yeah.
right? But let's see. 2x over x plus 1 here, maybe minus 3 here. Let's square this. Oh, clearly you have y is equal to 2, right?
Y equals to
And you have x is equal to
-1.
-1. Okay, so let's see the square. So, does it have y is equal to 2?
No.
So it's not guaranteed. Because look at it, if you squared it, you're likely to have 4x squared as the highest degree, right? And here you're likely to have 1x squared. So you might be talking about y is equal to 4 instead. Let's just check. Can you see that? So it's not guaranteed, but the vertical is guaranteed. Okay? So that's why it was silent. Not to talk about it. It could be. Let's look at the logarithmic function quickly. We haven't done exponential logarithmic function, so I will understand if you are not able to figure it out. Of course, they meet at the intercept, the x-intercept. That's a constant. Okay, they always meet there.
So it doesn't exist now.
What?
It doesn't exist in y equals 1, doesn't it?
No, because you don't know y is equal
Wait, so
to.
I think they do play at some point.
When y is equal to 1,
Yes,
Can you go to the right side, please?
what?
Go to the-
Like here?
No, no, go.
Yeah. Really.
Oh, they give me the guy. Oh my god. They meet
They
again.
interact at y
I
equals-
missed that.
They what?
They interact in their side y equals 1.
Oh yeah. True. So again, when y is equal to 1, if it exists, of course, do you know why y is equal to 1 here? Log 10 base 10.
Ah.
And if you have 1 already, you square 1, you still get 1. So again, if the function can give you y is equal to 1, yes. Okay. Now, quickly, let me run through this. Okay, one thing you will notice here. Between this range, one is greater than the other.
Yeah.
Outside this range, you might not be that lucky. Look at if there exists. So I put here between -1 and 1. Okay, let's say that in the exponential also. Look at between -1 and 1. The blue one is closer to the x-axis than the red. Okay? The square function is closer. But outside that, it's not the same. That's a point that I also wrote in your summary for you. Let's see if that works for this also. Between -1 and 1, the square one is the purple. You see, it is closer than the green.
Yeah.
Yes.
It's not a mirror. This is not, it's not a reflection. So you can see this is closer to this than this one. Okay? Especially for non-linear or quadratic one. Let's see if we can notice that for these functions too. Between -1 and 1, can you see? The square, which is the black one, is closer to the x-axis.
Yeah.
Okay? So when you are sketching, you will really want to put this point in mind. Between -1 and 1, okay, maybe this is not so obvious to see. We can't really say this easily. Okay? But let's look at it here. At least picture it from here. Oh, we don't have that in this case. We don't have that in this case. Can you see? Do we? Between -1 and 1. We don't. It is? Because the square is green.
Yeah.
Between -1 and 1, the square is not closer. For this one especially. Do you understand what I mean?
Yeah.
So it doesn't work for this reciprocal one. So there are distinct features for different types of functions. So let me run through this quickly. Oh, guys, class may be dismissed. You can go. We are just about to finish up here. Quickly, listen, please, quiet. So, one, if it is linear, y and 1 and 0 expected, even quadratic, 1 and 0 is expected. But again, if it exists. Okay? Again, wherever your x-intercept is where the square function turns. And as expected, if one intersects, if the graph of y has a y-intercept of 0b, the square will have b squared. It's like when you substitute x equal to 0, you get a b. In the other one, it automatically becomes b squared. So if you want to sketch, take note of those parts. So I'll give you an instance. This is the worksheet I'm giving you. This is 0, 2, right? So you will expect the intercept of the other one to be 0, 4. Jensen!
Oh, sorry.
Come on! You will expect the other one at 0, 4. Understand? And this point is going to be the turning point. Hello?
Yeah.
So it's crossing from here. It's going to turn. Then don't forget your y is equal to 1 and all the whatnot. They're going to meet at y is equal to 1. Hello?
Yeah.
So it's coming from here. They're going to meet at y is equal to 1. The deuce is going to turn here and it's going to go back.
Yeah.
And being linear, you expect that to be a quadratic. Quadratic is parabola. A parabola is meant to be symmetric. So you want to picture your axis of symmetry, which will be on what?
On the
X is equal to what?
3.
3. So you really want to make sure the other figure is symmetrical on the other side. Things like that. Okay? So quickly, quadratic one, again, you see this AB, then AB squared. 0B and 0B squared. So you really want to take note of that. Now these are general points for other functions that are not quadratic or linear. And what are the general points? Again, the y coordinate of 0 or 1 are invariant. Invariant means it does not change, it does not move. We're going to be talking about that in transformation with the general class next week. Okay, invariant points. It means it does not move, it means it's the same. Which is similar to what we have been talking about. They have the same y is equal to 0 and y is equal to 1. It's the same thing we have been talking about. Again, f of x touches x-axis at the intercept. We've talked about this. This is just a general for other functions. It will always lie above the x-axis. Or a worst case scenario, it will touch. It's not going to go below the x-axis for the square one. Because there's no way you can square a number and you get negative, right?
Yeah.
Aha. So quickly, the vertical asymptote remains the same, but the horizontal asymptote is not. It's not.
The same.
Don't say it's not the same. It could be the same in some cases.
It's not always.
It's not always the same. It's not guaranteed. In the case of 2 over y or 2 over x, I think we got the same thing.
Yeah.
Right? Because you have 1. Even when you square 1, you still get 1.
Yeah.
But when you have 2, you are getting 4.
Yeah.
You might investigate that if the vertical, if the horizontal asymptote is a, does it mean the other is a squared? You investigate that. Understand? You investigate that. And this is the last part. Between minus 0, minus 1 and 1, the graph of f of x squared is closer to the x-axis than the f itself. But outside that interval is the other way around. So when you are sketching, you want to have that in mind. And we have seen a few, except in that other function, that we couldn't see that. So you really want to have that in mind. Okay? Your linear, your quadratic, especially algebraic functions, you will expect that to happen. I think even in logarithmic function, we notice that too. This is the only place where our stuff is not the same. Can you see? Okay. If you look at this, this is closer here too. But let's see the other, sorry, after this I'll let you go. Let's see this one. This actually works.
Yeah.
This is the only one that doesn't. That's a weird thing. Okay? So this, so in general, you will expect that. Okay? Look at this, you see, the blue is very close, within the range. So when this is given, and you are trying to draw the other one, you want to make sure it's closer by distance. Understand? So please take note of that. Pass this round. Check more information here. Are they 4? No. How many? Wait. Please, can you check that? Okay, yeah. Okay, because this is because we are going to meet over the weekend, right?
Yeah.
So I'll be talking about this over the weekend. Talking about it. It's not that there's no investigation for this one. So we will just observe together. And this is the worksheet on this one. I intentionally did not put the equation responsible for these graphs because I wanted to sketch it. Okay, I wanted to sketch it and see. Understand? Any question, please? What happened to asymptote?
Yeah, so
Take a marker.
I've seen graphs like
Can you move this here, Kelly?
and then is it still an asymptote?
Yes.
If it never touches. But it goes through.
But it goes through it.
I see what you mean. Now, it only goes through at that point, right?
Yeah.
Further away, it doesn't touch. So what we can do is to restrict the domain and regard it as an asymptote.
Oh, so if we're only talking about this area.
So we can restrict the domain from that point upward. Then we can say yes, it's an asymptote.
Okay.
We came across a question also last year with the current Form 6. And there was this debate about, is this still an asymptote? And we agree that yes, it is. Because it still is something, asymptote is, what does it approach as x approaches infinity? This is not x is equal to infinity yet. So we are not saying it never touches. We are saying as x becomes large. That is why the idea of asymptote, we always say when x becomes large, y tends to what? That what is your asymptote. So this is probably when x is equal to 2, minus 1, 0, 10, not when it becomes large. So as you move further, what does this graph become closer to?
So as long as it at infinity, it doesn't.
It's at
touch.
infinity.
Okay.
That is it. So asymptote does not mean it will never cross. I think that's where most people may have a misconception. It could touch at the point.
Yeah.
But we are saying as x becomes large, at infinity, what does this graph try to approach? Okay, so like, there are some exceptional cases. It will have crossed somewhere, and at infinity, it changes its mind and it's coming back and it's approaching something, but it never touches that thing. All right. So yes, you can regard that as the asymptote.
So if you have a linear graph, can you say that at positive infinity, the also approaches positive infinity?
Say that again. A linear graph. Yeah.
So at positive infinity,
Yeah, it's trivia. This is trivia. Do you agree? For this line, as x becomes large, y becomes large. A linear graph is, in this case, for example, is m positive, right? Plus c. So it's going to diverge. It does not converge. Understand? Even for negative, it will still diverge, but in the negative sense. So that will be negative infinity this time. Understand?
Yep.
Any other questions?
could you say it has an asymptote at infinity?
No, this we can't say that.
No.
Asymptote is the line that it never touch, and infinity is not a number. You need to say the line y is equal to k,
Okay. Yeah.
but you can't say y is equal to infinity. All right? Because infinity is not a number. It's a concept to describe the biggest number that can ever be imagined, which is never imagined. I remember that almost cost my group some points in the university. We're presenting something, and my late teacher, oh my God, my mentor, somebody wrote A infinity. You know, we are talking about A1, A2, A3, A infinity, and he said, is this a number? And one of my colleagues said, yes. And he was almost taking off our point, and I said, no, sir, infinity is not a, because he told us, he was just trying to check if we remember. As long as somebody in your group can defend it, it gives you a spark our point. And there was this, whole argument about, oh, maybe you present it, this person present that, and I wanted to present it, but there was this debate about, no, don't present it, let, the smart boys present it. Okay, we the dummies will keep quiet. Then eventually one of the dummies had to rescue the group. It was so funny, because I really wanted to present it, but then I kind of understand fears of people sometimes. So, infinity is not a number, it's a concept. We can use that to describe the biggest, like, what can this become in the event that this continues indefinitely. So it's that concept. It's not like, oh, it's a number k, it's a number 2. Otherwise, you could have said that infinity minus infinity is equal to 0. If it is a number. Because this law, excuse me sir, we're still recording.
Oh, my bad.
Because this property exists for numbers. 0 is additive identity. So when a number and its additive inverse meet, they become the identity. Remember your function. F composed with F inverse gives what? X. And this X is known as? This X is known as what?
The identity.
The identity function. The same way numbers. K plus minus k gives you 0 because they are inverses in addition. So you get the additive identity. Similarly, multiplication, k times what?
1 over k.
1 over k gives you what? 1. So
One.
these are inverses in multiplication, and this is the multiplicative what?
Identity.
Identity. So unless we can establish that this is a number and they are inverses of each other, and this is the additive identity, then maybe yes. But unfortunately, this is not a number. There was this joke I thought I sent to you already. It's a meme on Instagram. This minus this is equal to 0. Like, yes, but no. Okay?
Yeah.
All right, thank you very much. Carolina, can you help turn that off?
No punch getting screen time.
Yeah, I'm gonna get paid.
You press the red button.
Press this one.
Katina.
You press the biggest